which we do every month, once a month. And so the format, is 3 talks, and we're going to discuss. So the first talk of today is by Parth. Não posso falar ainda. Não posso falar agora. So the first talk is by Dr. Parth Bambhaniya. Hope the name is correct. He recently arrived from India, where he got his PhD from the University of Charuzat, which is in Mumbai, so close to the Tata Institute. And I never been to India, so I really want to go to And so he's working at the Institute of Astronomy and Geophysics at the University of São Paulo with Professor Elizabeth Lampino. He's an expert in singularities. Yeah, he's going to talk about this very provocative title. Are we sure it's a supermassive black hole? Thank you.
Yeah, thank you for the nice introduction. Yeah, so the title is, you can see it's a very a big one, but yeah, it should be the interesting talk, like how the question comes in our minds. Maybe you all understand my voice, right? Understand? Okay. So I'm talking about are we sure about it's a supermassive black hole at the heart of our galaxy? So the outline of talk is like I will give a brief introduction about the literature review, what Penrose and the Hawking does for the singularity theorems, and how the theoretical foundation of the black holes come. And then we'll talk about the gravitational collapse, and then the observational, the possibilities about the accretion shadow and the relativistic orbits of our galactic center. So, and then we'll make some good conclusion. So I will just talk about the brief overview of the how the life of the life cycle of the star will evolve, because of we all know from stellar nebula there are it's like a factory of stars where from stars are the born, and there are multiple stars depending on their mass. There are some average and the massive stars and smaller stars. Depending on its mass, the end state of these stars are different. For example, in the Chandrasekhar, gave the notion of if there is a sun-like star. For example, there is Chandrasekhar limit of the massive star is like a 1.4 times solar mass. And then if the sun, as the star is like a sun, then the end state will, So you can see the end state is it becomes like a white dwarf. Okay, so it's a very stable star when the star exhausts its nuclear fuel, and then there is the pressure which can halt further gravitational collapse, and that pressure is known as the electron deceleration pressure. And then if there is a massive star, and then it becomes like it has to be gone through this cycle from massive stars, red supergiant, and then supernova. And we all know the remainder of the supernova can be neutron star, and then the black holes. Again, it depends on how much the mass of the star is there. So it's just an overview of the life cycle of star, and then. Okay, so the question is like one of the most important key issues nowadays in the astrophysics and cosmology, like what happens when the massive star dies? Because the Chandrasekhar already pointed out the star collapse and stable configuration limit, like the Chandrasekhar limit for the white dwarf, and then the continual gravitational collapse of the massive star, how it will work with the the end state. So there was like after the discovery or after the theory of general relativity published by the Einstein, there was the first solution given by the Carl Schwarzschild.
I don't know why it's not there. So we're trying to push. Sometimes it works, sometimes it doesn't.
Yeah. So the first solution of the Einstein field equation is given in the 1916 by Schwarzschild, and it is like a vacuum solution of the Einstein field equation. No matter, no pressure, and you can see like the systematic gravitational collapse studied by the Oppenheimer, Snyder, and in 1939, and that is by the assumption of spherical symmetry. The total pressure should be zero, and like if you consider the homogeneous profile of the spherical symmetry. This is the artistic pressure. It's not like it's just showing the dust collapse. Dust is like a particle where the internal interaction between the particle is neglected. So if the total pressure is zero, it's called dust collapse. So if the star is totally homogeneous like this, and there is no pressure, and the density should be homogeneous within the star, then the end state of the collapsing star will be a black hole.
So it dissipates energy, right? So it's dust, but has electromagnetic charges.
No, because all the nuclear fuel, inside the star core, there is a nuclear fusion process is going on. And because of the nuclear fusion process, all the enormous energy going outside. And the gravity is dominant, the tendency of the gravity is going to be collapse. But there is some equilibrium between, between the gravity and the outside pressure. But then, if the core area, the fusion process will stop because of, we need some higher temperature for further collapse and further fusion process. So then there is gravity will dominate and it's collapse. So if there is no further, the fusion process, no outside energy come out, and then the gravity will totally dominate and star becomes like a very compact region. That's we call the singularity. And there is one region is called event horizon. I will come to that point, but the key point is that the black hole modeling from the theory side is based on some ideal assumptions. So you could ask, okay, what's the ideal assumption? So at that time in 1939, it's very difficult to solve the Einstein field equations. So they took the Einstein equation is working the Einstein equation has a trace energy tensor component. This T mu nu, like you can see, the energy density part and the radial and tangential pressures. So they took two assumptions. They have considered the homogeneous density profile of the collapsing star. The second one is they neglected the total pressures. So after considering this T mu nu, or you can see the T component of the T, R, theta, and phi of the trace energy tensor, if you consider the zero, it will be easy to solve the Einstein field equation. And then it becomes a black hole. And the black hole solution is totally vacuum outside, no matter part and all this. But the good thing is that it's the ideal solution of the Einstein field equations. And then you can see this figure in terms of like the time in the vertical side and you can see this figure like how the collapsing matter evolve in the time. This is the time axis, and this is the radius of the collapsing matter depicted in the 2D. So you can see how the collapsing matter work. If it start evolving the time, there will be like event horizon here. This one, the first my arrow like this one. The event horizon start to form from here, and then the singularity will form later after the event horizon formation. So this is the scenario, and this curved line is singularity, space-time singularity. So the singularity is the region. Okay, so we have a question like, what's the singularity? The singularity is the region where all the volume element of any field becomes infinitesimally vanished, and where all the non-space-like geodesy, for example, if you are looking for the particle trajectory or particle geodesy or light geodesy, all this geodesy will incomplete at the point of singularity. But I would rather say the singularity is point where the general theory of relativity breakdown. It's not a point of the space-time manifold itself. So you can say it's a boundary of the space-time. And you can say, oh, all the physics laws will break down at the singularity, and general relativity not work. So we can avoid this singularity by going, by improving some theory in the quantum gravity and all this. But all the singularity I'm talking about is the classical singularities. So there are certain, the model like this Oppenheimer, Snyder, and Dutt about this one. And then now you can look what happens if we consider the inhomogeneous matter profile. This is not the star profile. I took these pictures from the Freeman Dyson something, but to illustrate the idea how the inhomogeneity work inside the star, because in the center of the star, like the high density region at the core of the star, and then you go from center to the surface of the star, the density will decrease. It depends on what the density function you have choose. Okay,
So if you assume spherical symmetry, even
again, yeah, the spherical symmetry, because when the star start to collapse, it's spherical symmetry we have to consider because of the tidal force and all the radial forces are considered. But for the sake of the comparison with the Oppenheimer and Snyder Dutt collapse model, we just worked out the density part, not pressure. Still, it is dust collapse. You can see here. Still, it is dust collapse. But only we have worked out is just the density inhomogeneity. So then you can see the here the singularity will form little earlier than the event horizon and apparent horizon, and then all the outgoing null geodesic come out from the singularity to the asymptotic observer. So you can observe like we can get some the light rays from the nearby singularity region. Okay, I'm saying the nearby singularity region, not from the singularity, because as I said, the singularity is the fundamental limit of the general field relativity. Yes.
So in the original case, you are basically mathematically you're assuming in the metrics spherical symmetry,
Yeah.
and your T mu is 0.
Yeah.
And now you are putting a T mu that is 0, but the metric is isotropic.
No, the T mu is not 0. T mu the
tensor. It's
yeah, this part is not 0, like this one, the row.
okay.
The first in the first part in the Oppenheimer Snyder the row is 0.
Okay. Okay.
Like for the homogeneity.
Okay. Okay.
But now I am taking some function of row.
So it's like a radial row function.
Yeah, row is the
You
function
specify
of something. Yeah, yeah, yeah.
But then, can you go to the next slide with the singularity? So that the point in which the singularity starts depends on your density profile that you're assuming. Okay.
Yeah, you can free to choose your density profile. For example, in this case, in this paper, particularly in this paper, they have choose rho 0 plus rho 2 r squared for this inhomogeneous dust collapse. So you can choose, this is the LTV, the collapse, general spherical symmetric LTV collapse scenario, where, the inhomogeneity is considered by considering some specific function of rho. So it's just for the interesting case, but it's again, it's a momentarily naked. The singularity is momentarily, it's not like an event. Sorry, it's like an event ladder. It's not an object. Because ultimately you can see after the singularity is visible, then if you go again into the time evolution, the event horizon will appear here and it will be covered by the event horizon.
Okay, so can you push it? Like, how far can you push the naked singularity with this? Because I guess so, since this parameterization depends on the density profile that you're putting, can you like push the singularity?
Not too much, because of if you it depends on how much the inhomogeneity profile you are considering. So, but in this case, it's just like the moment before the formation of the event horizon. So it's like it's event like it's just event for the singularity, and some information come out from the singularity, and then it will be covered by the event horizon. But the interesting part is you can avoid this the formation of event horizon when you consider the non-zero pressure as well, because we haven't considered any non-zero pressure here. It's just a dust collapse. The eventually dust collapse will come to into the singularity. There will be no any pressure which can halt further gravitational collapse. So you have to be considered some non-zero pressures. So I will come to that object-like singularities in this later slides. But this is the initial, the idea was given in the 1939. Maybe I am making some mistake. Okay, so for the inhomogeneity dust collapse, it was given in 1939 by Professor Pankaj Joshi and the ICTP. So he was my PhD supervisor. So for the getting, the illustration and basic ideas of how the pressures and, the densities are working with the Einstein field equation, you can see here. The left-hand part, like given of the Einstein field equation is totally, the represent the curvature geometry of the space-time manifold. And the right-hand part here, T mu is represent what type of field or matter are you considering. So that depends on, the T mu is the stress energy tensor, where, if you consider the spherical symmetry, then only the diagonal components are there. All the off-diagonal components will vanish. So for the off-diagonal component, you have to consider the rotation like curved black holes. So for the simplicity, just the Oppenheimer, Snyder, and Gauss consider this rho, PR, P theta, and P0. So, this right-hand side of the Einstein equation is completely zero. So there is no any matter, no any field. So that's why the Schwarzschild solution and the curved black hole is totally vacuum outside the black holes. So this is just for the understanding and clear view. Now you see. Yeah.
One question, but in the previous slides, you had the cosmological constant or not? Because the
Yeah,
cosmological
if
constant.
you consider the large scale, the manifold or space-time for the large scale, like for example, FLRW, then you have to consider the cosmological constant for the dark energy and expansion of the universe. But the object like black hole and the singularities, and if you are considering the center, the compact object like the galactic center, like say there is A star, so then you can skip this.
So you are extending around the Sitter metric. That's true, because in Cosmos it's not a solution of the for the cosmological constant, right?
Yeah.
So okay.
So this is the general, the space-time metric given here, for spherical and symmetry. And you can see, again, this the T mu new component for the energy density and pressure are given here. And all this, the equation for the general gravitational collapse. I'm not going into the detail of these equations,
So
but
this is a matter double null.
yeah. But general spherical symmetric, more general, what the Oppenheimer side and the consider. And then, now, as you said, depending on the what type of, the profile of the density and pressure you are considering, it depends on what initial condition are you considering. Your end state will totally depend on your initial condition, whether it is a black hole or singularity. It depends on your initial condition, what you are choosing. So we have scanned this, this plot like for what different kinds of parameters you have a naked singularity and black hole. You can see the filled dot is for the naked singularity region, and the empty circle is for the black hole formation as an end state. And
Naked singularity evolves to a black hole in the end.
yeah, but if it is a dust collapse, the condition is the dust collapse.
And in this plot, the parameters are some parameterization or your density functions.
Density, yeah, it's the density.
But it's like for a specific choice of the parameter, like a function that you're parameterizing this.
There are you can have a different kinds of the function of the density, and you can have the different velocity profile, how much velocity is required for the collapsing. There are velocity and the density function you have to choose. So depending on this parameter, you can scan this the parameterization.
So these parameters are in the energy momentum tensor only. And what is M3 and E5?
It's just like it's a scale they have given for the parameterization, but I'm not
Of the metric or the energy momentum?
no. I'm not sure about this M3 and M5. I just yeah. But it's just like the coordinate they have considered for this parameterized, but I'm not sure what's the detail of this M3 and E3. But yeah, of course you can find in this paper detail because this work is done by the Professor Joshi, and I'm just following the work. And yeah, okay. So okay. So this is just the introduction part for my presentation, and it's very just for the curiosity. In 1997, in the time in the New York Times, they like have you can see here the battle is the bad he made with two professors at the California Institute of Technology was that naked singularities could not exist. And now it seems they could, maybe. So, yeah, it was in the, we can see the 1997. The battle, already started there, and it's just for fun. And then, the Professor Pankaj Joshi had, extensive discussion with the space-time singularity with Roger Penrose, who got the Nobel Prize in 2020 about the Robert prediction of this gravitational collapse theory and singularity. So yeah, and then the Scientific American article made a cover story about the naked singularities and all. And there are Cambridge and Oxford monographs on this gravitational collapse and space-time singularity, and also the global aspect in gravitation. These are the books you can refer for more detail of the Professor Pankaj Joshi's work. And the funny thing is that someone is made some series or movie on the title of the naked singularity. I don't know what's the meaning, but it was obviously not on the astronomy part. It is like some crime series or something like The funny thing is like, but yeah. Now come to the point, like in the Nobel Prize award of the 2020 in physics, Roger Penrose, got the Nobel Prize for the discovery that the black hole formation is a Robert prediction of the general theory of relativity. And these two guys like Reinhard Gengels and Andre Geis for the discovery of the supermassive compact object. I don't know why they avoid the word of the black hole, but they consider the supermassive compact object Sagittarius A star at the center of our galaxy. It's just a recent, it's not an older discovery. So I'm skeptical. Why all this? So that's why I have a question like, what should be the nature of Sagittarius A star at our galactic center, and how one can estimate the space-time structure or the causal structure of the geometry of Sagittarius A star. So is there any way to make some good things and good progress in this direction? So that's why you can see this video. The Roger Penrose himself corrected this Nobel, citation. Like I made, the contribution and the formation of the singularity, not for that.
All this time later, you get the Nobel Prize in 2020. And did that come as a surprise to you? Has it made any difference to how you work or the opportunities you have?
No, I don't think so. Oh, 2020 was a good thing and a bad thing. Because of the lockdown, I was able to sort of work out certain ideas that were buzzing around in my head, and I hadn't had a chance to work. And so I wrote down some notes and around colleagues, and this did end up being a paper. This was, I would say, the good thing. The bad thing was getting the Nobel Prize, because it stopped the whole thing dead. I'm being unfair here, but trying that. What the citation said was black holes are a robust prediction of Einstein's general theory of relativity. What I really showed was singularities are a robust prediction of general relativity. See, the thing that we don't know is whether you get singularities that are hidden behind horizons, which is the black hole, and that's what we believe, or whether you get naked ones, it's singularities which are just there and information could come out of them. And I, in a sort of way, rather hoped in my wild sort of view that maybe naked singularities might occur. But as far as I'm aware, there is still no proof. General community sort of resigned to the idea is what you get this black hole.
Yeah.
Which in a sense is a more boring situation.
Obviously, yeah,
Yeah, so you see, he himself corrected his Nobel Prize citation, and it is expected that it would be a naked singularity because he really showed the formation of singularity, but not sure like whether there is an event horizon or Robert prediction of the black hole. So this is the exciting thing. What we it's just a recent interview, with the New Scientist channel.
So what about the picture of the Event Horizon telescope?
Yeah. I understand your curiosity, but yeah, okay. So it's the ongoing battle. I don't know how.
You should press escape and start in the box.
Okay, thanks.
So just to clarify, because I mean, I come from a more numerical cosmology background, so these things I didn't knew that it's math. So just to confirm, this statement is true. Like mathematically, after putting this kind of solution of dust with a certain profile,
Yeah.
you can obtain mathematically within GR a naked singularity.
Within GR, yeah, it's true.
That's a statement.
No, but there is no more beyond this dust collapse. You know, there are.
No, yeah, yeah. So there's, I guess, then you like
Right.
to try to make the thing physically.
Yeah.
You need to include other things, but mathematically within GR, if you put those things, you know that you should obtain a naked singularity.
Because,
Okay.
because you know, as I shown in this figure, in this slide, you can see after this Oppenheimer-Snyder dust collapse in 1939, Penrose made a statement on the cosmic sensor sequence.
Yeah.
But the singularity doesn't sit there forever. I mean, it's,
Yeah, yeah.
Yeah.
There
Yeah, but the cosmic sensor conjecture is like not proven yet, and you know, it's still no proof of the cosmic sensor. Like the cosmic sensor conjecture says, oh, all the you know the gravitational collapse, you know come to the singularity, and then it is always hidden
Yeah.
behind the event horizon. Okay, so this is that's why we call the conjecture.
Yeah.
Yeah.
But the thing is that you can find space-time, like an event in space-time, in which you find a singularity that is not surrounded by an event horizon from an. Okay.
even Hawking considered defeat.
Yeah.
Hawking
But
considered
this is the case for this is the case for the only dust collapse.
Yeah, no, but I mean, just as a mathematical statement was a thing that I was
Yeah.
completely unaware, and it's very powerful.
Yeah.
Now we go to physics.
point that
Okay.
it doesn't have a phenomenological impact because those singularities they don't make on a macroscopic timescale.
So the lifetime of that singularity up to the rise of
Not right, I mean, the time they stay naked,
Yes.
it's beyond.
microscopic, it's not macroscopic.
When you say microscopic, I mean, it's like lower than like a Planck time scale or something like that, or is it, or you can have it like what's microscopic? It is
I
observable.
think he's going to discuss.
Okay,
this.
yes.
I will, because there are certain things right now regarding. So the important question in the black hole and in the singularity is like, you know, what are the observational astrophysical? Okay. The formation of the naked singularities and black hole is fine, but what is the observational implications? And you know, it appears that the answer is indeed affirmative. So you know, like. So there are certain cases we can look for the observation. For example, you can see the shadow and accretion disk properties. You know, there are several S stars are orbiting around our Milky Way galactic center. It's called S stars by the gravity and you know the Andre Gage group. And you know the gravitational waves. We just look for. We have looked for you know just only for the black holes and neutron star. We haven't looked for any you know like the case of the singularities. There are some tidal forces effect because of the horizonless object. There might be some different effect of the tidal disintegration of the star and tidal force effects. And you know the powerful relativistic jets like a gamma ray burst and all the neutron flux coming out like quasars and blazars, all the high energetic you know the process is going on, and we have the observational proof, but we haven't you know we are trying to with the black holes and you know we need the observation data. But then, you know, this collaboration of the Event Horizon Telescope made, you know, the very interesting contribution into the black hole physics. Like they have made, you know, built the several observatory and make array to get like Earth-sized telescope for observation of the to focus our galactic center and M87, and then they, you know. Obtain these two interesting figure of the black hole. So the first one is represent the center of M87 galaxy, and the second is our own galaxy. But the crucial thing is that the shadow arises because of the presence of the photon sphere. It's not confirmed. The shadow is because of the event horizon. And come to the point, what is the photon sphere and what is the event horizon? But be in mind, this shadow here represent this dark region. It is a radius of the photon sphere, and it is at 3n. R is equal to 3n. while the event horizon is at r is equal to, for the Schwarzschild it is r is equal to 2n. And for the rotating case is below r is equal to 2n. So now how one can make a notion of the space-time. For example, the star like a sun, we have a totally vacuum space-time outside, you can see here, outside the compact objects. But, you know, we are mimicking this center of our galaxy with the vacuum solution like a Schwarzschild and curve. This is totally purely vacuum outside. But now if you represent the galactic center, there are, you know, the matter concentration at the center, like you can see here, it's not a vacuum. If you consider the center is like a compact object as a secondary star, and there are many concentrated matter, like a baryonic matter and dark matter, you can consider. So to mimic the galactic center, we have to consider like the most probable the solution of the space-time to present the galactic center. That's why, you know, this model, the obtained by Professor Joshi Malapari and Ramesh Narayan is also from, you know, the Harvard University and is a part of this EHT observation collaboration. And, you know, like this model obtained, like as we said previously, we just consider the inhomogeneity in the density. Now, in this model, we consider the, you know, the non-zero tangential pressures. Let's consider there is no zero pressures, because when the star and, you know, the clouds of the matter is collapsing, there is some interaction between the particles and, you know, dust and whatever the particle, anisotropic matter. We don't know the constituent of the matter yet, but it could be anisotropic, perfect fluid, dust, or, you know, the scalar field. So they obtain this matrix, and you can see here these RV represent the equilibrium configuration of the matter constitute. It's not totally collapsed into the singularity. There is some equilibrium like a galaxy, and, you know, this M naught represent the, you know, the intensity of the total mass, and you can consider the inside as a like some like the equilibrium like this metric. This is called the J-main metric, and outside is totally vacuum in the asymptotic region. So you can match with the Schwarzschild like a metric. Here, M naught RV is considered to be 2M for the massing condition. And C, we have considered for this model, the rho is a function of M naught by R squared. While, you know, the tangential pressure is non-zero. Just to be, you know, start with some realistic model, we consider the PR is equal to 0. But in the JMN2 model, the both the total pressures are, you know, the identical, and it's perfect fluid solutions. And again, these scenarios given by the Janice, Newman, and Vinicor in 1968. This paper you can refer for it. I am sure for. But they have given the scalar field solution of the Einstein field equation, where you can see this Q is represent the minimal coupling of the scalar field, and it's a massless. So they have given some the potential of the scalar field, and then they obtain this solution like a Schwarzschild. If you consider Q is equal to 0, this scalar field becomes the Schwarzschild spacetime. The Schwarzschild is vacuum. Now, if you are introducing some scalar field in the Schwarzschild background, and then it becomes the Janice, Newman, Vinicor naked singularity model. Because in this model and this previous model, yeah, in this J-min is also naked singularity. There is no horizon, and in this JNW, it is also naked singularity. There is no horizon. So, to perform the the shadow imaging and the accretion properties, we need to solve the null geodesic here, and we just consider the simplest scenario for the spherical symmetric and static spacetime. So you can see there is the conservation of energy and angular momentum equation in the general term. And then I'm not going to detail in the equation, but just I'm giving the overview how we obtain the the numerical imaging of the shadow. So using this condition, all the general theory of relativity, you will find the effective potential of null geodesic. And this effective potential is very much important for the how the light or photon will behave in the background geometry. So therefore, you can see the shadow formation condition we have got here. So the photon sphere here is the this point is the photon sphere called it's unstable the unstable circular orbits of the light geodesics. So, which is, the depicted at 3M in the Schwarzschild black holes. But this is not the case. We have also showed in this paper, like the photon sphere is not only the property to formation of the shadow. Because if there is, any compact objects and your light, becomes plunge into the, your light going to plunge into the center at r is equal to 0. This plot represents the V effective versus R, and your light will go at r is equal to 0. Okay, then the dark region will form. In the shadow image you can see here, what is the shadow? Everybody knows, everybody have notion like this is the shadow. No, this is the accretion disk. The shadow is only the dark region. So this dark region represents the shadow of black holes. This the bright region is just because of the accretion matters and the intensity of the accretion matter. So the shadow, for the shadow formation, you need to be have, if there is a photon sphere, like the scenario of the figure 1a, if there is a photon sphere, then after this photon sphere radius, the light will plunge into the center and this dark region will form. But what happens if there is no photon sphere? Or if you have upper bound, for example, the existence of an upper bound of the effective potential of the null geodesic can also have a shadow, because the light also will go to the singularity. And then in this case, the shadow radius will, the very small compared to what we have in the black hole case. But the interesting thing is that if there is a photon sphere and your effective potential is diverse near the horizon or the singularity, then there will be no shadow, because all the light going inside will scatter back because of the barrier of the effective potential of null geodesic. So these are the conditions we are, we are working on that. It is in preparation, and now you can see this is the illustration schematic figure for the Schwarzschild black hole.
Sorry, so the different behaviors, because you have a parameter in your model that you're changing this parameter and then you can.
No, this effective potential behavior is because of the background geometry. Because you have a different kinds of background geometry. For example, if you have a black hole like geometry, then you will have like a photon sphere of the effective potential here. And then if you have like a horizon less compact object or some, some star, then this could be the possibility of the, the effective potential. And there is other like warm solutions and other, the exotic objects that have like a photon sphere, but don't have, the upper bound, the effective potential will diverse.
So this can happen in GR.
In GR. Whatever I'm talking here in this presentation, this is totally within GR. I'm not considering any modified gravity, any exotic matter, any quantum field.
But you have parameters that are not from GR, right? You have B's.
What?
You don't have parameters in the metric that's not coming from GR?
No. How can you say is it a solution of the GR or not? So if the Einstein-Hilbert action will not change,
okay,
so then it's the solution of GR.
Okay, so the modification is in the metric.
Yeah.
I mean, you arrange the matter so to have
The modification in the initial condition of the collapsing, the matter.
Oh, but I have. So first, how do you, I mean, is it easy to see how the shaping of this potential tells if you have a shadow or not?
Yeah, because of if you have the effective potential equation like this from the null geodesic calculation, this is the GTT and G55 for the general space-time matrix. Now, you can incorporate your metric tensor component over here, and you will get your specific effective potential. So whatever the the geometry.
But what is the mathematical condition to have the shadow? I don't understand.
Oh, okay. For the shadow in the black hole case, you have like the effective potential. Effective potential should be like this. The first derivative of the effective potential, it gives the maxima, like the maxima and minima, and then the photon sphere is the unstable photon orbits. So that's why we need the second derivative of the effective potential should be less than 0. So this is the condition for having the photon sphere.
This is the condition for having the
photon sphere. Yeah.
Okay, but then you go to the next slide.
Yeah.
You still have shadow without the local maximum.
Yeah, but we still have a shadow here in this case because of your potential is like there is upper bound. So your light will goes into the center and towards the singularity or in the center, whatever you call. Yeah. So this is the behavior of the
So, and why then the question, why there is no shadow in the third?
because of there is a still photon sphere, but your potential near the horizon or the singularity diverges infinitely.
Okay, okay.
So the light will not go into center, and you will not get any darker region.
Two questions. In the right one, what would like, I guess that the event horizon, like in the right plot, would be below your photon sphere.
The event horizon?
Like where you are putting the, yeah, because like once that you transfer like the event horizon scale, so that you have as a function of R.
Yeah.
At one R, you would have the event.
Yeah. So
One-
look for the. I'm just saying that what is the what radius the event at what radius the event horizon and what radius the photon sphere
Okay.
is in this figure. You can see.
Okay.
So this is the for the Schwarzschild black hole for the understanding. Like you can see the innermost stable circular orbit at the 6th end. And then the event horizon, this dark region of the black hole is at 2n. But the photon sphere radius is 3n. You can see here. So how can you confirm by the shadow imaging of the photon sphere? Is it a black hole or not? Because all other compact objects have a shadow like identical like this, and I come to this point. So basically this shadow arises because of the null geodesic how it behaves. But this just the the illustration of the understanding how the null geodesic behave in the curved space-time, depending on what type of curved geometry background you are considering, and how the gravitational lensing of the light is working behind the formation of the shadow and accretion, as you can see. This is the case for the spherical symmetric case, so you will get the structural like things. So, and then we have studied these shadow properties in the black holes compared to the horizonless objects like a naked singularities. And you can see here, this is the shadow of accretion disk. We studied the the radiative emission accretion model in this paper. And then these actually numerical things did by the Saurabh, is a PhD student at the Max Planck Institute currently. And we found that we got the identical shadow of the naked singularity with the black hole when the naked singularity have the photon sphere. Because naked singularity have some parameter space where the photon sphere can exist or not. So it depending on the parameter space. For this parameter space of the M naught should be like a greater than 2/3 and less than 1, or we get the photon sphere at the same radius as the Schwarzschild have, and it's identical to those of the black holes, static black holes. And similarly, we did for the scalar field solution of Janisch-Newman Wittig naked singularity, but the radius of the shadow is slightly smaller compared to the black hole and this naked. Because of we introduced some scalar field, and again this radius of this shadows depending on the how much scalar field, how much intensity of the scalar field are you considering.
So that scalar field is just the distribution of the density that you were.
Yes, distribution of the massless scalar field.
Okay.
Yeah. So but if you are considering the lightest scalar field, for example, if you consider 10⁻⁻20 or 25 something, for example, or 50. Doesn't matter how much smaller scalar field are you considered, but there will be no horizon. That's the case. So, and also we have shown a similar approach with you can see how much the difference in the intensity we can get from the black hole to the singularity. So we have shown the cross-sectional horizontal intensity for the model imaging of this first row represents the black hole. Second is the naked singularity, and the difference of the first and second row is given here. So there is almost no difference in the different, the frequency range. So EST is currently now observing the 230 gigahertz frequency range. So almost negligible, and the EST are unable to find this smallest difference. And then currently I found the paper with this EHT group members, and they have the performed GRMSD in the horizonless rotating black holes, for example, Kerr naked singularity, or we can call a super spinor. So they have they have found some some interesting difference in the GR image circulation. You can see here in the intensity distribution of the black hole accretion and the naked singularity. They found that the accretion matter close enough to the singularity repels due to the effective potential. Again, this behavior is totally depends on the effective potential of the background geometry, and this prevents matter from reaching to the naked singularity and forms some quasi-spherical symmetric density distribution around. And unlike the accretion flow around the black hole, this would be the the distinguishable features in this matter or the shadow imaging. So I'm putting this screenshot of the Event Horizon Telescope paper. This Event Horizon Telescope paper L17, 2020 for the discovery of the secondary space star, and they have clearly mentioned in their paper, like more strikingly, for the same approximate luminosity as the secondary space star at 200 gigahertz, accretion flows onto these singularities have spectra nearly identical to those of a Schwarzschild black hole, and indicating that this naked singularity, Joshimala Narayan, with a photon sphere may be one of the best possible black hole mimickers for the Sagittarius A star. And then the possibility that the Sagittarius A star is a naked singularity cannot be ruled out based on the metric test we described in these sections. I'm not saying it's just the EST screenshot paper for the curiosity.
So they have collaborators in this.
Yeah, Ramesh Narayan, this German solution is one of the authors. Ramesh Narayan he was the expert in the accretion and shadow. And then there is a Prashant, the postdoc, and so they all are open for the the other compact object, which are the horizonless. So it's good thing they are open for the other possibilities. So then it follows that the existence of and observation of the shadow is not sufficient. So what's the next? Okay, so there is some observation of the S stars, which are orbiting our Milky Way galactic center. Here there are certain S star I have considered from these papers, from the gravity collaboration, and these WKM observatory led by the Gates. So there are the most curious stars is S2 because it has less error in these astrometric positions. So I have considered this Astro star as a good candidate because all other stars have the more error in these observations. So then we studied we can study how in the gravity space-time geometry curvature this star will behave. The star will not have the similar elliptical orbit. It will precede in some particular directions. So it would be anti-clockwise or clockwise, depending on what type of geometry I am considering. So I'm going to talk about how the star precision, angle, and this, the shift of the orbit, the work with the theoretical modeling, and how you can fit your observational data with the theoretical in the next part.
So Schwarzschild doesn't have precession.
So it has precision, but it has a particular type of. Yeah,
The different precession, and that you can distinguish between the two.
that's why actually the gravity group done these things with the Schwarzschild precision. So this is again the vacuum solution, and we have to study all the time like geodesics. I have given here for the rotating, the space-time geometry, which is the spherical, not spherical symmetric. Actually, it's actually rotating, and again, we have to use all the general formalism for deriving the general orbit equation. So I skip this theoretical part here, but the interesting point is that you can see now your point is, if your star will start from this phi is equal to 0 from this red dot, it will precede going in the anti-clockwise, and then after the greater than 2 pi rotation, your next minimum approach will be greater than 2 pi rotation. And your orbit again will shift in this direction, So your particle is orbiting anti-clockwise, and your orbit also precedes in anti-clockwise direction. So that's we called prograde or positive risk. But this is the scenario for the vacuum solution. If you consider some matter distribution in the background geometry, for example, these horizonless objects, then you can see your particle starts from pi is equal to 0 and it reaches before 2 pi angular distance travel. And your next orbit will shift in this direction, this clockwise. your particle, orbiting anti-clockwise, your orbit will shift anti-clockwise. That's called retrograde or negative precision. I'm not sure how much time I have, but maybe I
Like 5 minutes?
Okay, I will go a little fast. So I have studied again in this paper with the curved black hole whether the spin will affect this precision or not. We never found any retrograde precision in the curved black holes, and we proved this with this the by solution of the orbit equations. And then also we have studied this type of behavior in the several rotating naked similarity. You can see clearly here. This black dotted is for the curved black hole, and this green is for the naked singularity. This black, the first orbit is this, the second is this. You can see the orbit will shift anti-clockwise. Again, the particle is orbiting the anti-clockwise. So it's a program. But in the naked singularity, this is the first orbit. The particle is anti-clockwise, and then the orbit will shift clockwise. So this is the retrograde precision we found for certain parameter space of the distribution of matter. And then we used these theoretical modeling with the observation data using this, the capillary orbit approximation using this delays, the transformation with the, how the original orbit can be seen in the apparent orbit. We have to do some transformation mathematically, and then this is the result from the gravity collaboration in 2020. They have done this black dot is representing the position of the star in the astrometric and declination. So they have fit this observation data with the Schwarzschild geometrical orbit. And then they have published this paper, but then we did the similar analysis with the naked singularity. And it's also best fitted with the observational data. So again, this is the question, because we have estimated several parameters for this best fitting using the MCMC and the well-known the chi-square and all the statistical procedure. And now the conclusion of this talk is like a recent theoretical development in black hole physics. There is a question such as, are we sure it's a supermassive black hole at the out of our galaxy? Or what about the information paradox? If there is an event horizon, and these horizon-less compact object could be a possible candidate which might fit in the space-time structure of the galactic center, and it could be like a future aspect we can see for the quantum star, whether it could be not singularity or not black holes. Like if we consider some quantum gravity theory, then it could be like a quantum star, and the singularity can be resolved. And then the interesting things for the Big Bang singularity as well, because the Big Bang singularity is a space lag, and it is also naked. It's not covered by the horizon. So we have to believe the singularity could be naked. So from the Big Bang is the best the example for the naked singularities. And from all these, the arguments we have, there exist the major key issues in the black hole physics, the general relativity. And you can see what happened at the singularity, we don't know. And are all singularities hidden behind event horizon? This scientific American cover story article by Paulo is very famous in these days. And what happens to all the information which goes inside the black hole? This is the information paradox. So we have these major challenges in the black hole physics, and I really appreciate for your time and attention and the questions.
So, yeah, if there are any questions.
Yes, I'm worried about the matter you're putting around the central object. So first, is it stable? Second, what is its density?
Yeah, so recently we have, submitted the paper in the archive where we have studied the quasi-normal modes for the stability, for check the stability of this model, and it's stable under the small perturbation.
So the matter is orbiting and doesn't fall.
Yeah,
What's
it's
its
equilibrium configuration.
sorry? What's its density?
The density of matter?
Yes, because if it's high density, then it should emit.
No, so the density profile we have given here for the J-band case, you can see it's a m by r square. We have considered this matter density profile, this one. Yeah, the rho is a m by r square, is the function of r. So,
Yeah, but I mean, is it sufficiently rare that
It's very less interacting with the, it's very, it's not like high dense matter. The central object is a compact and then there is a fine matter distribution, not totally vacuum.
Okay, but it's what?
It's anisotropic matter.
So, but can you see a figure for density of the matter that you need to support the singularity?
Yeah, for
Given
the,
the size, the mass of the black hole is that one, because we measure from gravitation.
yeah, for the support of the matter as an equilibrium, we
Yeah.
consider this, the tangential pressure.
Yeah, but what are the figures for this matter, for this density? I mean, how much matter is there?
You could choose whatever, the function of the rho you would like. It depends on the mathematical model. Because, this is not like the highly, the concentrated matter which affects too much the observations. Like it's like a swastika outside this
Of course, I mean, the gravitation is fine, but I mean, if you put a lot of gas around, then it should heat up, it should do a lot of things. So
Yeah,
I
so
want to know what is the density and the mass you put in this gas.
So in the inference plot, don't you?
maybe I did not get your.
I mean, you have this central object, which is 4 million solar masses. Okay.
Yeah.
Now you're telling me, okay, it's not 4 million in the black hole, but it's something in the central object, and then it's the rest of the
Yeah,
mass
so
is
yeah, okay.
infused in
So
this matter.
we are considering the, the total mass of this the distribution within the RB. It's like a, it's a ADM mass, like within the cell of this.
Yeah, but I mean, not all the mass is in the central object. Some of it is in this gas
Yeah,
or powder or however you want. How much is in the gas?
How much in the gas?
Yeah, 1%, 1 per million, 10 to minus 6, half of it. How much of the mass is in this gas or powder?
So we haven't any, the numerical number yet, because it's just a function of the rho here considered, but the radius of this matter is up to the 3m, below the 3m.
Okay, it's below the 3, so roughly.
It's not like
Same order of the mass.
yeah, it's not asymptotically
Okay.
flat.
But then again, this mass is 10 to the minus 10 of the total mass, or is it a sizable fraction?
You can consider this mass as identical to those the black hole.
It's a sizable fraction of the mass of the black. Okay, but then the huge concentration of matter, it should heat up. I mean,
No,
if
the
it
total,
rises-
the huge concentration at the center. It's
no,
not.
but at 3M, if you put a sizable fraction of the would be black hole at 3M, so you put you mean million of solar masses on a distance of million kilometers. Okay,
So, for example, within 3m, what I understand from this modeling is within 3m, the center is like a 98% concentration of mass, and then the remaining 1 or 2% are distribution within the atom. So that's the density profile.
okay, still you're telling me that it's not high density enough.
Yeah, it's not enough high density within the RB. It's like the high density is at the center again, because the singularity form at the center. So
So this distribution, I didn't get it that, so in the, beyond the mass that you're putting in the black hole, you would have this other distribution, and 98% would be within what distance to the?
98% is like you can consider at the central compact object, and then the distribution is remaining.
So it would be 2% of.
1 or 2, yeah. So depending on the distribution of the density matter. But again, this density distribution affect your observations. But you are free to choose your matter distribution profile.
Related question, is it stable to the emission of waves? Because the scalar field you can emit at the monopole, right? So during the collapse, you could emit some energy. Is it stable to its emission as well?
Yeah, it is dynamically stable in the equilibrium during the gravitational collapse. But the outside is totally like asymptotically, you can consider the vacuum as a swastika. And also, in these two negative singularities with the JW and this JNM, the quasi-normal modes are studied by the perturbation of the scalar, electromagnetic, and gravitational perturbation in the package. And it is stable under up to the 6th order of the WKB. Yeah.
I have one more question.
It's too naive. Don't really have much to bring to this subject. But your presentation is about this model where it would have a possible mimicry of a black hole behavior. So right, have a central object with a naked singularity, and it mimics the the behavior of a black hole. We are not sure whether Sagittarius is actually a black hole. It could be this other object. Is that all right?
Yeah.
Okay, so my question is, what, I don't know if you talked about this, if you did, I'm sorry, I couldn't catch it, but what features of black holes this model cannot mimic?
Yeah, because of all the information going inside the horizon. For example, if you are like they asked me about the perturbation. So the black hole has the shield, like a membrane of the event horizon. So everything goes inside the black hole, we don't know. So we have the geometry outside the black holes, like a Schwarzschild curve. So we have a solution of Einstein field equation. It's a vacuum solution of the outside the black holes. It's not within. We are not looking for the inner geometry right for this image. So everything goes inside the black holes. So there will be information parables.
Sorry.
There would be information parables where all this information going.
Oh, it's a way to,
Yeah.
it's a way to actually go through, it's to go around.
Yeah.
Okay, good. Thank you.
One, I think this is super basic because I didn't understood. Yes. So on one hand, we have sparse solution. On the other, which would be like a general case, we have care solution. I didn't fully get if with this modified, well, in the way in which you include in this other solution, these other shells of matter, you can also consider like a rotating case.
Yeah, we have. Yeah, we have the rotating case of this solution as such. Because, for example, this you can see this the orbit we have done in the rotating naked singularities. I didn't speak about. You can see this one. These orbits we have studied in the rotating naked singularities model.
Okay.
So we have a solution of the rotating naked singularities, like a curve. So we can mimic the curve black hole orbit as well, like we did it with this test black holes.
And in these cases, when you're showing the positive
Yeah,
perception or
positive,
negative, I guess that's that's parameterized from the M or some parameter.
Yeah, yeah.
Is there like a point in which it changes?
Yeah, we have like a parameter space in the metric. For example, in the Schwarzschild black hole, we have only the mass parameter. We can play with the mass, whatever we have to do. But we didn't find, in any vacuum solutions like this retrograde precision. It's not a property of this retrograde precision is not property of the negative singularity alone. It could be for the black hole, but black hole should be with the matter distribution, not vacuum. Like if you study the Schwarzschild and Kerr black holes, you would not get any retrograde precision because we have the calculated everything in these two papers. So you need some matter distribution to get the dynamical friction and some effect of the matter density on to get the retrograde precision. That's why in this figure you can see the angular distance traveled by the particle is come before again to the minimum approach before 2π rotation. And in this case, you can see it's after 2π angular.
Yeah, but you should like in that model that your free parameter or your free parameters, you should be able to tune them to recover this partial. So there's like a point in which you have like zero.
Yeah. So that's why we have the considering the parameter space, most possible parameter space. For example, you can see here the angular momentum and whatever the stable orbit, stable bound orbit. That's the case. The condition for the stable bound orbit we have given here in this. Let's see here. Okay. You have to find the stable bound orbit, like a circular or elliptical. And for these conditions, you have to consider this parameter space.
Okay.
And you can scan this parameter space throughout all the possible scenarios.
I don't know if this is a very nice question, but with this new method, we can we still find a solution with the scattering problem and find the quasi-normal modes of this singularity.
Yeah, you could
Find the same procedure of Schwarzschild black hole, like a Reed-Wheeler and the equation.
Yeah.
We can follow the same procedure.
Yeah, we just did recently with the WKB method, and you could use the Brownian method for the time domain evolution, and then it could be give you like if there is some matter distribution, it could be partially reflected your waves, and it can give the echoes-like properties in the gravitational waves. For example, in the black hole case, it's totally invisible, it's totally absorbed by the event horizon. But if there is some like, the reflective surface or some matter distribution, you would have some partial scattering or reflection. And due to these properties, you can have, the echoes in the oscillation of the waves. So that's again, the observational properties.
But, okay, but it will be the same procedure as turning this R into Tortor's coordinate, right?
Yeah.
Because the problem is the event horizon, but when you do, or use negative singularity or use Tortor's coordinate, we just vanished the event horizon and just put him in the minus.
But yeah, in the negative singularity case, all the plane waves vanish at the singularity.
Sorry?
In this case, in the negative singularity case, this all your like in the Swasi case, your perturbation vanishes at the event horizon.
Yes.
But without horizonless object, your perturbation vanishes at the singularity.
Okay, nice. And one more question, because I don't know, it's curiosity. When you are doing the scattering problem, you have to take some considerations in the Schwarzschild problem. Nothing goes out of the black hole and nothing goes from the infinity to the black holes. So you can resolve your scattering problem with wave plane equations. The solution would be plane waves. But in this case, if you don't have event horizon, you still have to consider something goes out, right?
Yeah. But there is a limitation of the parameter space. For example, how these shadows is formed because of if there is some turning point and all other things, then the shadow of the dark region would not have some the extra luminosity should be. But there is the interesting point in this negative singularity. There is the photon sphere. When the photon sphere they have, there is no turning for those parameter space. They don't have any turning point. It will totally plunge into the singularity. So,
Okay. And this turning point will change from 2M in Schwarzschild to 3M.
yeah.
Okay.
Exactly. This is the the modeling scenario. So
Okay.
that's why we are getting the identical images of the black holes.
Nice.
Yeah.
Okay, so there were lots of discussions, which is really good.
Yeah, it's really nice question because we are working on and debating on this issue right now. So
Okay, so we can talk more later.
yeah.
Is here in São Paulo.
Yeah, you can visit.
Yeah.
The ING and astronomy. The PhD student, my colleague is here.
Okay, so let's then part again. Short break, we'll come back at 11:30. Let's take 20 minutes. And relax a little bit. You're next. We can do some first information.
Yeah. It was very good. Yeah, thanks.
My